Hi, my name is Ishant Chattopadhyay. I'm an assistant professor in the computer science department at Cornell University. I joined Cornell in 2018, so this is my third year here. So my main area of research is theoretical computer science. And within this particular area, I've worked a lot on the specific questions related to the use of randomness in computation and various questions related to it. So randomness is used in a variety of ways in computer science, like in designing fast algorithms, in cryptography, in distributed computing, and many other areas. And there are fundamental questions around it, like, is randomness truly necessary for designing fast algorithms? So there are central questions in complexity theory around this. In some cases, like in cryptography, we do know that randomness is required. And there are related questions like, how do you come up with pure random bits? Because in nature, it's hard to find such pure random bits. So these are some of the questions I've tackled, and I'm also actively thinking about these questions. So I started thinking about complexity theory or research in theoretical computer science when I was exposed to really beautiful courses as an undergraduate back in India in IIT Kanpur. What attracted me to this research area was that the kind of questions that was asked was really fundamental, and also it was really beautiful mathematically, and yeah, all this seemed really interesting for me to dig deeper and start learning more about this, and I've had a wonderful experience so far. And in this lecture, I'm going to talk about Turing reductions, which is going to be a new kind of reduction that you'll see. You have seen mapping reductions so far. And we'll also look at more powerful Turing machines, which are called as oracle Turing machines, which is intimately related to these Turing reductions. And all this will finally lead to more understanding on undecidability of problems. We'll see that there is a hierarchy among undecidable problems, and we'll have fun with these topics. Hi. Today's lecture is about a new kind of reductions called as Turing reductions. And the plan for the lecture is we'll learn about Turing reductions and also the related notion of Oracle Turing machines, which is a beautiful concept by itself. And we'll look at a couple of examples of doing Turing reductions between some of the languages which probably you have seen before. All right. Okay. So the plan is Turing reductions. And this is a new kind of reduction between languages. And this actually generalizes mapping reductions that I'm sure you have seen so far. All right, and it's my personal opinion, but I feel that Turing reductions are more intuitive. So arguably more intuitive. And the added bonus is that while we learn about Turing reductions, we'll also learn about this beautiful notion of Oracle Turing machines, which also generalize the notion of Turing machines that you have seen so far. So we'll learn about Oracle Turing machines. Okay, so let's actually start off today's lecture by learning and defining Oracle Turing machines. All right, so I'll try to formally define them and also build intuition along the way. So let B be any language an Oracle Turing machine M. Okay, so we'll say that Oracle Turing machine M with access to B. So we'll define it in the following way that we'll actually use the notation M with B on the superscript with Oracle access to B is a multi-tape Turing machine with some added features, which is it has a special tape. So it's a multi-tape Turing machine, right? And among its tapes, it has a special tape, which is the, we'll call it the Oracle tape, on which it asks queries of the form. Okay, so it has a special tape, which is the Oracle tape. And on this, it can ask queries of the form, does a string belong to B, right? And the important point is that gets answer in one computation step. All right. Before defining this more formally, so it's sort of like, it's exactly how it sounds like, you have a friend who is an Oracle who knows a lot of things. You can just query him and get an answer to a really difficult question. So in this way, so there's no restriction on B, right? B could be an undecidable language, an unrecognizable language. As long as your Turing machine M has Oracle access to B, it can just cheat and get answers to queries like, does a specific string belong to B, in just one computation step. So this is a very powerful generalization of the model of multi-tape Turing machines. And so if we want to define this more formally, so more formally, what happens is, M writes X on the tape, on the Oracle tape, and it asks the question by transitioning to state query. So it has a special state query on which it transitions and sort of asks the Oracle, like, hey, there's something written on the Oracle tape. Does the string belong to the language or not, right? The appropriate language which is defined by the Oracle. If X is in B, then M goes to the state Q yes, else M goes to Q no. And this is sort of, some formalism if you actually want to write down the transition table of this Turing machine. And, there are these three special states, there's a special tape and so on. So this can be very formally captured as you have seen for normal multi-tape Turing machines. And again, I do want to reiterate the fact that there's no restriction on what kind of language B can be, right? So it's a pretty general model. And as you'd expect, the more powerful B is, the more cool things your Turing machine can do. So here is a really simple observation, which is, B can be decided by an Oracle Turing machine M with Oracle access to B. All right, so this is almost trivial from the definition that, if I give you Oracle access to B, then I can design a Turing machine, which on input M just writes its input on the Oracle tape and gets the answer. So therefore, if B is, say, undecidable or even unrecognizable, MB decides B, right? So with Oracle access, you can, the class of languages which can be decided by Oracle Turing machines is strictly larger than the class of languages which can be decided by Turing machines which do not have Oracle access. Of course, it depends on the Oracle. And if, the Oracle is powerful enough, for example, B is undecidable, then you can actually decide much more, a much richer set of languages. All right, so that's what I want to say about this model. And using this model is kind of the key definition of this lecture, which is Turing reduction. So we'll say that, language A, Turing reduces to language B. So this is written as A Turing reduces to B. So if A can be decided by a Turing machine that has Oracle access to B. All right. So if you can, get membership queries to B in one computation step using this power, if you can come up with a Turing machine for A, then you say that A Turing reduces to B. All right. And this is kind of the key definition that we have for today's lecture. And
before thinking about more implications of what it means, what it implies for when A Turing reduces to B, let's actually do a couple of examples and try to get our hands dirty with Turing reductions. Okay, so the first example is kind of simple but really instructive, which is, okay, so define ATM to be MW. The tuple MW says that when run on W accepts the string W, and ATM is the complement language, and the claim is that ATM bar is Turing reducible to ATM. All right. So recall, the proof of this is not that difficult, but it's a really instructive example. Why is that? Well, recall that this language is Turing unrecognizable, whereas this language is recognizable, right? Of course, this is undecidable, but it's recognizable. So, you couldn't have done a mapping reduction from ATM bar to ATM. It's not possible because that would actually imply that ATM bar is recognizable. But Turing reductions actually is a strict generalization. It allows you to do these reductions from unrecognizable languages to recognizable languages. All right. Okay, so let's actually try to prove this. The proof is really easy. What would you do, right? You're trying to design a decider for ATM complement given Oracle access to ATM. Well, let's just do the obvious, which is, let's say the decider we are doing is TATM. So this on input MW uses Oracle access to ATM to check if MW belongs to ATM, right? And of course, so what it formally means is, given its input, it writes down the input on the Oracle tape and makes a query. And whatever answer it gets, it just flips the answer and outputs it, right? And output flipped answer. And I mean, this is trivially true because if MW is an ATM, it cannot be in its complement. And if it's in the complement, it cannot be in ATM, right? So clearly TATM is a decider for ATM complement. And its computation is literally just the time taken to write down its input on the Oracle tape, plus constant time, I guess, to get the Oracle answer and also output its answer. All right, so that was easy, but it also was instructive in the sense that you can Turing reduce unrecognizable languages to recognizable languages. All right, so let's try to do something slightly more complex, which is so again, familiar languages. So halt TM, which is the language of all MW, such that M halts on W, and ETM, which is all M, such that M does not accept any string, right? And suppose, let's try to prove that, so let's try to do a Turing reduction in one direction. So let's try to prove that ETM, Turing reduces to halt TM. All right. Okay. So what does it mean? It means that suppose you have Oracle access to halt TM. Can you use this to come up with a decider for ETM? All right, so let's actually try to do this. Suppose, the thing that we are trying to construct, the Turing machine that we are trying to construct is T. So this has access to halt TM. And it's supposed to be a decider for ETM. So its input is something like M. Okay, and the trick we are going to use for this is something along the lines of other Turing reductions that you may have seen before. So what we start off with is actually by coming up with a description of a different Turing machine, which depends, of course, on M. So construct a Turing machine N that on input X does the following. Okay, so we are coming up with a new Turing machine N based on M, which in the following way, that ignores input X. So N ignores its input X. And then what it does is it runs M parallelly on all inputs. And if M accepts a string, then N immediately halts and accepts X. So then N accepts X. All right. Okay. So I guess let's try to maybe qualify what it means for this part, what it means to run M parallelly on all strings. I'm sure by now you're familiar with the notion of enumerating over all finite strings that can be formed by an alphabet. So let S1, S2, dot, dot, Si, and so on be an enumeration of all finite length strings that you can form out of the alphabet. And at ith stage, where you have for I greater than 0, so it's a loop at the ith stage, run M on each of S1, run M on each of S1, S2, dot, dot, till Si for I computation steps. All right. So, I mean, it doesn't really make sense to start from 0, I guess, because the numbers have started from 1. So you take your Turing machine M and run on the first I strings of this enumeration for I computation steps. All right. So this is what it means for running M parallelly on all inputs. All right. Okay. So now what we have done is, okay, so to recap, we are trying to design a new Turing machine T, but we took a detour and came up with a description of a new Turing machine N. And now back to designing T. Okay, so given N, what we do is, so recall that T has access to halt Tm. So what it does is really simple. Uses Oracle to halt Tm to check if n comma 0, belongs to halt Tm. And then it just flips the answer that it gets from the Oracle query and outputs it. So if yes, output no, and else output yes. All right. So that completes the description of T, which is supposed to be a decider for ETM. And note that, so all that happens in the computation of T is given its input M, it writes down the description of this Turing machine N, which functions in the way it's described here, and then uses its Oracle query to check membership in halt, and this just flips the output, right? Okay, so why does this work? Well, suppose M accepts a string y, right? Suppose we are in the case where there is some string y which is accepted by M. So of course this means that M is not in ETM, right? Okay, and it better be the case that T also gives you the same answer. Well, let's see what happens. So if M accepts string y, then what does N do? N on input X, completely ignores its input, runs M on all inputs parallelly in this fashion. So it, when M is run parallelly on all inputs, it will happen that, M runs for the appropriate number of steps it requires to accept Y. So at some point, at some stage I, some large I, M is going to accept Y. And at that stage, N is going to accept X no matter what X is, right? So in this case, N accepts all strings, right? No matter what its input is, it's just going to accept it. Okay. So what can we say about the query n comma 0? Well, N accepts all strings, so N accepts 0 as well. So it belongs to halt TM, and hence, we answer, so the query Oracle query is yes, and this is flipped to no, and this is exactly what we want, right? Good. So in this case, T works as we wanted it to work. And now suppose M does not accept any string. Okay, so if M does not accept any string, what does N do on any input? Well, N ignores its input and continues to simulate M on strings, and it never stops, right? So it keeps looping. So in this case, N loops infinitely on all inputs, and therefore N0 is not in halt, which implies Oracle query is no, which implies T outputs yes, right? And in this case, when M does not accept any string, it is indeed the case that, M is in the language ETM, right? Because it does not accept any string. And that's exactly what T outputs. So this actually completes the proof that T is a decider for M, and hence completes the proof that, we have a Turing reduction that we wanted. All right, so this completes the second example, which was, slightly more tricky. And in the next lecture, we are going to see implications of, doing Turing reductions between two languages, and also see that there's, a hierarchy of undecidability. All right, see you in the next lecture. Hi, welcome to the second part of the lecture on Turing reductions. And today we'll also learn about a new topic, which is the hierarchy of undecidability. So to briefly recall, in previous class, we started off by defining this really beautiful notion of Oracle Turing machines, which generalizes the multi-tape Turing machine model that you have learned before. And then we defined what it means for a language to be Turing reducible to a different language. We saw a couple of examples of familiar languages that you have seen and how they're, Turing reducible among each other. And today's lecture is more going to focus on its implication. So let's start off with that. So the first important theorem that we are going to prove, it's relatively straightforward to prove, but it's really the implication of, Turing reducing one language to other, which is if a language A is Turing reducible to B and B is decidable, then A is decidable. All right. So this is kind of the main power of Turing reducing language A to B. That we could state it contrapositively stated. Contrapositively, it means that if A is Turing reducible to B, and we know that A is undecidable, then B is also undecidable. All right. So if you're trying to prove, so suppose you're given a language B and you're trying to prove that it's undecidable, then pick the favorite problem that you have that that is undecidable and show a Turing reduction from that language to the target language B, and that will prove that B is undecidable. Okay, so let's actually try to prove this theorem. It's relatively straightforward. So I'll just try to sketch the proof. And the proof sketch is essentially just the intuition that you have that so we are trying to prove that A is decidable, knowing that B is decidable. So suppose suppose MB decides A. Well, we do know that from just the definition of Turing reducibility, that since A is Turing reducible to B, it must be that there is an Oracle Turing machine with Oracle access to B that decides A, right? Now, for every Oracle call to B, you replace it with computation of the decider for B. All right, so given this Oracle Turing machine, now let's try to construct a new Turing machine, which is just a simple plain Turing machine without any Oracle access, which does the following, that whenever it tries to simulate this Oracle Turing machine, and whenever this Oracle Turing machine does an Oracle query, it just replaces that query with actually simulating computation of the decider for B, right? And why do you have a decider for B? It's, it's from this assumption that B is decidable. So there's a Turing machine which decides B. And in this way, you can, replace each Oracle call with computation of the decider to get, the answer to your Oracle query. And hence what you end up with is just a normal Turing machine which decides A, and this completes the proof sketch that given an Oracle Turing machine for A, you can actually convert it into a regular Turing machine for A. All right. So, for instance, in the previous lecture, we proved that ETM is Turing reducible to halt TM, right? So using this, what can we infer? We can infer that undecidability of ETM implies undecidability of halt TM, right? So suppose you know that ETM is undecidable, you have the Turing reduction from ETM to halt TM, it would imply the undecidability of halt TM. All right, and also an important observation is that such a theorem does not hold for recognizability. So it is not true. So not true. What is not true? That if A is Turing reducible to B and B is recognizable, then A is recognizable. So again, emphasis on it's not true. And what's a simple counterexample for this? Well, we already saw a counterexample in the previous class, which is, so what's the counter example? Well, you can take A to be ATM complement and B to be ATM. Well, we do know, as we saw in the previous class, that it's really simple to come up with a Turing reduction from ATM complement to ATM. But note that, this is recognizable, but this is not Turing recognizable. So this is unrecognizable. And this provides the necessary counterexample that you need to, see that it does not hold that, such a theorem's version does not hold for recognizable languages. Okay. All right. So that's kind of the key use of Turing reductions to prove undecidability of languages. And related to this, I mean, as you saw, we defined Turing reductions via Oracle Turing machines. And a very natural question to ask is the following. So the natural question to ask is, how powerful are Oracle Turing machines, right? Of course, one could say that, the power depends on which Oracle you have access to. But in a generic way, suppose, can we say anything about, the power of an Oracle Turing machine, irrespective of how powerful or expressive the Oracle is. And here is something which is pretty astonishing. But also, if you think a bit deeper, maybe it's kind of expected that for any Oracle B, there are languages that cannot be decided by any Turing machine with Oracle access to B. All right. And this kind of gives way to this hierarchy of undecidability that no matter how powerful the Oracle you have, there are languages out there which are beyond the scope of being decided by Turing machines with Oracle access to B. All right. And this is going to be the rest of this lecture. We'll actually, show examples of languages which are beyond scope of Turing machines with powerful oracles. So let's actually try to make this more precise. Let's make this more precise. All right, so define halt Tm prime to be mx such that m halts on x with Oracle access to halt Tm. All right, so this is kind of a generalization of the halting problem that you have seen, which is now you're reasoning about Oracle Turing machines. So M is an Oracle Turing machine which actually has Oracle access to halt Tm. And now you accept all tuples M comma X such that M halts on X, having access to halt Tm. And here is kind of the claim which says that, even powerful oracles are not useful sometimes. And the claim is that halt Tm prime cannot be decided by any Turing machine with Oracle access to halt Tm. All right, so it shows a specific language, halt Tm prime, which is beyond the scope of being decided by any Turing machine which has access to a powerful Oracle. It has access to halt Tm, which by itself is an undecidable language, right? All right, so let's actually try to prove this claim. It's a pretty powerful claim, right? So, Turing machines with powerful oracles also cannot decide some languages. Okay, and the proof is actually pretty similar to the way you proved, that the halting problem is undecidable. It uses diagonalization in a way that you have seen before. So it's similar to prove that halt Tm is undecidable and uses the technique of diagonalization. Okay, so let's actually go through the proof. Okay, so suppose for sake of contradiction that, Turing machine H with Oracle access to halt Tm decides halt Tm prime, right? So suppose, you have an Oracle Turing machine with access to the Oracle halt Tm and actually can decide halt Tm prime. Using this, let's consider a different different machine, consider a different Oracle Turing machine, which also has access to halt TM, that on input X does the following. So let MX be the Turing machine represented by X. So X is the string which is code for the Turing machine MX. So on input X, what T does is it simulates the machine H, which we assumed, is the decider for halt TM prime. So it simulates H on input MX, X. All right. And note that, this simulation is actually possible, right? This simulation is possible since T has Oracle access to halt TM. Right? So whenever, H makes an Oracle query to halt TM, T can do a similar query and, get the simulation through. And then it just does the usual trick of diagonalization, which is if H halt TM accepts the pair MX, X, then T halt goes into an infinite loop, and else, so let's number this 3. So else meaning if H halt actually rejects the input MX, X, then T halt accepts the input X. All right. So this is the entire description of T halt. So it's the usual diagonalization trick, which is kind of trying to contradict the working of H halt. And now to get the final contradiction, we do the following, which is what is the behavior of T halt on input T halt, so the code of T halt. So it's the string which corresponds to the code of T halt. And we'll show that any behavior is a contradiction, which will end up contradicting the existence of H halt. Okay, so for starters, suppose, that TH halt accepts the code to itself. So if TH halt accepts the input, what it means is that we are in this case, right? That's the only way T halt accepts an input. And in that case, it must be that H halt TM rejects the input T halt and the code to T halt, right? And if this is the case, well, if H halt rejects this, it means that T halt does not halt on the input t halt, the code to t halt. And this is a contradiction, right? Because we, started out with the assumption that, t halt accepts the input, the code to t halt, but now we arrived at the conclusion that it does not halt in this input, which is a contradiction. And the other case is also pretty similar. So suppose, so suppose t halt of tm does not accept the input, which is the code to itself. In this case, the claim is that, the only way t halt does not accept anything is if it's in this case, which is, t halt goes into an infinite loop. So what are the observations? So one is t halt goes into infinite loop, and also the fact that, we are in this case, which means that h of halt tm actually accepts the input, which is t halt and the code to t halt, right? And h halt accepting this means that, t halt halts sorry, it should have a few tms here. T halt of tm halts on the code t halt of tm, and 1, 2 contradict each other. All right. So in either case, we see that we arrive at a contradiction, which means that h halt cannot exist. And this completes the proof that, indeed, it's not possible to decide the language halt tm prime using any Turing machine which has Oracle access to halt tm. Okay, and the final concluding remark of today's lecture is that, okay, so we have shown that, there are languages out there that cannot be decided by Turing machines, which has access to halt tm, which has Oracle access to halt tm, and one can, continue in the same way, right? So similarly, one can show halt tm double prime, which is mw such that m halts on w with Oracle access to halt tm prime now is undecidable by Turing machines with Oracle access to halt tm prime. All right, so the proof is again similar, and one can generalize this to define halt tm triple prime, which has Oracle access to halt tm double prime now, and so on. So one can define an infinite hierarchy of undecidable problems. All right. Just to recap, in today's lecture, so we started out by seeing the implication of Turing reducing A to B. We showed that, if B is decidable, then A is decidable, and also saw the implication when taken contrapositively. Next, we did see a counterexample for the theorem not to hold for the recognizability. And finally, we said that, how powerful are Oracle Turing machines? Can there exist an Oracle which is powerful enough that, you can decide any language? And then we saw specific examples of constructing Oracle languages which are undecidable by Oracle Turing machines, which has access to halt TM. And then we said that we can generalize, in this fashion to build an infinite hierarchy of undecidable problems in this fashion, and hence there's no all-powerful Oracle which can access to which can, decide all languages. All right, thanks.